Okay, I think we should get started. So my name is Mandic. I'm a professor here at the School of Physics and Astronomy, and I work with Vipin and Shashi in our data science initiative. Welcome everybody to the synthesis panel. We have 6 panelists, and you've actually met all of them. They've participated in the workshop so far, and we'll reintroduce them in a minute. Each of them has been present for the entirety of the workshop, and for each of them has taken 2 questions or prompts through which that they thought about throughout the workshop. So they basically try to synthesize what they hear in this workshop through that particular lens or lenses. So we have this slide deck of, which has grown to about 16 slides organically over the last 2 days, and I'm excited to share that with you. We'll go through the panelists one at a time, and since we're fashionably late, I know we promised 5 minutes, but let's see if we can do maybe 3 minutes per panelist. We'll start with Srinivas here. Srinivas, if you can maybe briefly introduce yourself and then just launch into your...
Sure, yeah. My name is Srinivas Aluru. I'm from Georgia Tech, and since I'm partly responsible for why we are fashionably late, I'll see if I can be quick. I'm going to address a couple of 3 questions, actually. So let me start off with question 1. What are the most compelling, strategic, and potentially transformative Gen AI research questions that we could ask? So what I learned from this meeting, listening to all the presentations, is that there are like 2 grand challenge problems here that we could address. So the first one is about, can we transform AI from a prediction, Gen AI in particular, from being a mere prediction tool to a co-pilot for theoretical discovery? So let me elaborate on that a little bit. So if you look at the scientific breakthroughs that are made so far, such as AlphaFold for protein folding, or AlphaGenome for finding the effect of SNPs, single nucleotide polymorphisms, or weather forecasting simulations like systems like Aurora, GraphCast, Prithvi, etc. They're all fantastic prediction models. However, what we lost are theoretical insights. So AlphaFold folds. Everybody loves the way it folds. We know the answers, but we haven't really learned anything new in terms of how proteins fold because of AlphaFold. Now, AI interpretability may help a little bit, but it only explains how a network reaches its output, but it doesn't connect these explanations to the domain zones. So the question is, can we use Gen AI to somehow discover fundamental principles and mechanisms that reflect the predictions that Gen AI systems are making, so that the humans are not used to just consulting AI as an oracle, but also develop a better insight into the domain itself. So that's one grand challenge. A second thing is there is a need for accelerating the development of scientifically grounded generative AI systems. So many of you are using Gen AI in your science, but you're also finding a lot of loopholes. So to take a stock, we have already seen remarkable progress in representing complex and high dimensional distributions. But the performance sometimes seems to digress when the data is sparse or noisy, and still a lot of progress is needed to properly enforce physical constraints and conservation laws, etc. And also, these models are computationally intensive, and when you try to use them in the real world, you often have to sacrifice either accuracy or uncertainty quantification and things like that. So accelerating research in this direction would be a good idea. The second question I want to address is, what are the recurring themes for Gen AI that transcend applications, that cut across many applications, and what are the needs, and how does that tie into White House action plans? So I have a big list here, so I'll go through it very quickly. One thing that was touched upon in many domains here is the need for development of AI-ready testbeds. There are disparate and fragmented data sets in your domain. They're often created in specific application contexts. There are challenges for harmonizing the data, making the data discoverable, and also generalizing what kind of data helps us build Gen AI systems that have generality, etc. So this comes under the White House Build World-Class Scientific Data Sets theme, and that is something that is recognized as important by many of you. The second thing is foundation models for integrating multi-model high-dimensional data, and also physics-constrained exploration of vast design spaces. Another common theme here is the digital twins for natural and engineered systems. And an interesting twist that is important in some domains, such as neuroscience, is using AI-driven techniques to study natural systems. We saw an example of that, where AI-driven pattern recognition is used to sort of figure out the brain activity in response to different things. And finally, the development of AI cyber infrastructure itself, and not just the hardware cyber infrastructure, but also software cyber infrastructure to support the entire scientific discovery lifecycle, starting from design of experiment, data analysis, to investigation of alternative models and integration of Gen AI with classical methods. All of these things, I think multiple domains could use such software to accelerate, and we could leverage our common need to answer these questions in a way that's broadly applicable. And I'll stop with a brief answer to question 8, which is what are the pros and cons of the myriad Gen AI techniques that have been developed. I'm not going to answer this. What are all these publications for? Hopefully they have all answered this to some extent. But I think the most important need of the hour is to let the users decide. So if we accelerate the scientific software infrastructure for building models, for experimenting and reasoning with multiple models, then I think people can pick and choose, and we have a better knowledge over time of what would work best for what types of problems and so forth. And obviously there are efforts already, both commercial companies like Weights and Biases, which is now part of CoreWeave, and also open source platforms like MLflow. I think accelerating these would be nice.
Thank you very much, Srinivas. So, Baskar, if you like, you can speak from there, or
Yes.
come up here,
Yep.
whatever you like.
First of all, I think this was a thank you for organizing this, Vipin and crew. This was a wonderful opportunity to meet people and also immerse myself into the Gen AI what next questions, right? And so for the past two days, I think the highlights here are, and probably resonate with everyone. One is creating simulation data sets, right? So if from a generative AI perspective, collecting high throughput experimental data for various disciplines may not be possible, may be suboptimal. So creating synthetic data, whatever the synthetic data means, simulation data sets would be critical. And then identifying canonical problems, right? So geometry or like, and Vipin was talking about the traveling salesman problem as one canonical problem that could drive the discipline. Identifying canonical problems would be nice to have from an AI for science perspective. Second is, and this is something that Anant and other people talked about, and Ganesh also talked about, right? So there's generalizability of Gen AI tools, but then with that we need some formal guarantees, right? So, and then this is a rich area from an applied math perspective, right? So can we show convergence rates if you have a mesh? Can we provide non-vacuous generalization bounds, trade-offs, and how much data is needed, data sufficiency, thinking about that, right? So that we can invest resources into collecting 1 million data points or 10 million data points, right? As long as you know what that curve look like, even empirically what that curve looks like, right? That'd be good. And then this is something that was a very nice initial kickoff by Anuj and others on terms of what are the different ways of rigorously injecting knowledge into the Gen AI tools. And yeah, there are systematic ways of doing this, right? So that we learned architectures, losses, post-train conditions, and so on. And then the key thing from a science perspective is this UQ, maybe going beyond verification and validation and giving calibrated intervals of uncertainty so that we know when to get more data, when to trust the system, and so on, right? So these are the 4 key themes that seem to resonate from question 2. And everything in blue there on the screen is basically how they link to the AI action plan. I think there's a lot of things here that link to the AI action plan. And then in terms of question 7 was are there challenges for incorporating different kinds of priors? And so here I think there's very interesting. So we talked about 3 or 4 ways of integrating priors, right? So in terms of architecture, in terms of loss functions, in terms of post-training. So is there a roadmap, checklist, right? So for this kind of problem, I should use this. For this kind of problem, I should use this and this, perhaps, right? So thinking about that would be super useful, because we talked about materials, we talked about agriculture, we talked about ecology, and each of them have different flavors of these. Second is, we have GenAI models that could be general purpose, but then we want to maybe fine-tune them for specific applications. So there could be a trade-off or a fight between model and constraints, or one type of constraint or the other type of constraints. So how do we actually think about this, right? So from a GenAI perspective, and can we come up with formal maze in which we say, oh, if you have this kind of generative AI model and this kind of equations, or if this kind of system, this is how you want to integrate, ensure that there's no constraint dissatisfaction, and so on. Right? Finally, there's this question about, I think Raj talked about steerability and generalizability and so on. So how do you think about modular designs, right? So Lego-like designs that integrate like hybrid neurosymbolic methods, and then how do you also integrate process-based differentiable models, right? So we have a gamut of tools. How do you integrate them in formal ways? And then finally, priors alter error behavior. So understanding this, right? So especially when you have a Gen AI tool with a certain distribution, and then you add constraints to it, the distribution changes perhaps, and how understanding that would be critical from a mission critical perspective. So,
Okay, thank you, Baskar. Our next panelist is Paul.
Great, thank you.
Can you introduce yourself briefly? Can you introduce yourself briefly?
Yes. I'm Paul Hanson. I'm from the University of Wisconsin in Madison, and I'm an ecosystems ecologist. And I just want to reiterate, I guess, what a great couple of days this has been, what a privilege it's been to be here, and how exciting from the domain side to see all the advancements and to learn and to be able to imagine what we can do on the domain side within the AI realm with collaboration. And so I was charged with coming up with a few questions that sort of synthesized a few perspectives over the last couple of days, and specifically from the domain side, so we could imagine more than one domain scientist being part of these questions that are being asked. And I've got two groups of questions on two different slides here. So the first have to do with data. There were a few different data repositories that were represented here today, and the question is about how we can grow the corpus, or how we can include the growing corpus of domain data in generative AI, and do it in a way that really engages the domains that produce those data through provenance tracking, providing credit, but more importantly, feeding back to the domains itself, so that when scientists understand how their contributions from the countless hours that they've spent collecting these data, how they can inform and contribute to computer science and AI science, that it feeds back in ways that makes that a positive experience and kind of grows those interactions. The second question is what advancements will enable Gen AI to fully use multimodal data and data with missing data? This seems to be a theme that crosses almost every application, and of course in ecology this is first and foremost, from everything from genes right up to satellites. The second slide is a little bit more about a human-oriented approach. The first question is, what would it take for Gen AI to not only match, but surpass the predictive skill of a highly trained domain scientist? This resonates, I think, a little bit with what came out in the health discussion, where you train a system on a population. And now how do you decide, and what are the implications for applying it to individuals? And I think a question that's sort of posed this way resonates with anybody who comes out of the domain sciences too. A theme that comes up over and over again, and it's already come up a couple of times in this panel, is the inclusion of expertise from domains in generative AI. And here I've just highlighted three different areas: knowledge-guided machine learning, reinforcement learning, and then evaluation of both the frameworks and the outcomes of the generative AI. And then just a question that's near and dear to me, which is extreme value distributions, and how could we possibly do a better job at extreme events? So thank you very much.
Thank you, Paul. Jarvis?
All right, so again, I'm Jarvis Haupt. I'm with the University of Minnesota, Department of Electrical and Computer Engineering. So a couple of things that, as I was, this was a great workshop. I really enjoyed, and thank you to the organizers. I was thinking about these questions. They were kind of posed ahead of time, and I was using this to distill with my lens some of the responses here. So I guess, I could just read from this. I guess these will be distributed. But the first question was, a lot of applications are concerned with things like hallucinations, uncertainty, and safety considerations. Are there kind of cross-cutting ideas? Are there ideas that are universal that could be transferred across? A couple of things. First of all, just to challenge the premise of the question a bit, it was brought up in an earlier session that not all hallucinations may be bad, right? If we allow a little bit more leeway in this, it may lead to new discoveries. I think we do this for ourselves as well. So I don't know if we call it hallucinations, but at least the creative thinking is not without its virtues. Some of the other ideas would be, for instance, there's a lot of models that we have access to now. If you're thinking of large language models, there's Claude and the Llama models and ChatGPT and Gemini and things like this. They're all trained slightly differently, so you could use outputs of one model to validate another model. So these might be ways of trying to reduce uncertainty. It's kind of like a mixture of experts type validation, but maybe slightly different. You could also use models to kind of scrutinize each other, not just validate, but also police. One would produce a response and you'd say, is this legitimate, or does it adhere to whatever principle I'm thinking of, whether it's a physical principle or an ethical principle. One of the concepts that came up as well was this idea of sensitivity analysis, and I think that this is an interesting insight because in a lot of ways, if you think of classic machine learning type problems, maybe a supervised learning kind of problem, you're training on discrete data, right? You have instances, and what you're hoping is that you're behaving kind of sensibly off of those instances, right? The generalization is kind of the value add. And I think sensitivity analysis could be a good way to kind of try to quantify this, to look at what's happening locally in the vicinity of maybe the training data points or farther away. But this idea of like trying to understand what was sort of learned from the data, which was discrete, to something that we're going to generalize off that grid. And then another idea that came up was this idea of negative examples, that maybe we don't really have those kind of pervasive in our society, tabulated in the same way that other kind of collections of information are, but they could be useful here. I think that's worth exploring to see. If I go to the next slide, the second question, what are possibilities for cross-domain complementarities for addressing data scarcity? So one that came up earlier today, I'll just start from the bottom here, was this idea that your data set might be structurally similar to something else. So the example that my colleague Sachin and ECE discussed was they were looking at this EDA task, but they didn't have access to a wealth of training data because of IP restrictions, so they trained on street data maps, which is a really kind of clever idea. Some of the other things that I was thinking about is, again, just to reiterate some of the concepts I talked about yesterday, is this idea of problem decomposition. If the problems themselves might not be holistically related, but if you can decompose each problem into subtasks, there might be similarities in subtasks. So it's almost like we're doing a physical latent embedding ourselves, right? We're saying, this is similar to that, so I'm going to try to share insights here. And then just more generally, this idea of finding potentially unifying latent space representations. Just one other thing that I wanted to say here, kind of as I was thinking about the panel and the structure that we were presented here, I wondered if it's also a microcosm. So this is a situation where, again, we were provided the questions ahead of time. It was kind of like view the workshop through the lens of these questions. And I don't know if many of us get that many opportunities to do that. I was thinking about trying to pose questions like that to the students in my class, but it sort of made me wonder, just kind of as a parting thought maybe, with some of these kind of applications, would it be useful to train with the questions in mind ahead of time, right? Instead of looking at, for instance, an autoregressive model or the autoregressive kind of characteristics of a large language model, just looking for latent connections in text, say, I'm interested ultimately in answering this question, right? It's sort of like you're baking in attention ahead of time. Just a thought, but it was something that kind of was a microcosm for this modality, and I thought I would share it. So, thank you.
Thank you, Jarvis. Lior?
Lior Horesh. I'm the head of the Mathematics and Theoretical Computer Science department at IBM Research. I was tasked with 2 questions, and I added 1 bonus. But beforehand, I would like to thank all of you because I learned a lot during this 2 days of workshop from you and from my peers, so I'm grateful being here. So the first question was around interpretability as a common theme across many Gen AI applications in different domains. Are there any recurring approaches or methods that can address that, and are there any ideas that can be carried out across different domains? And few ideas and propositions that at least I could conceive. One is that when we look into the specific primitives that are transferable between one domain and another, whether we use attention mechanism, we use structured state space models, gradient-based methods, or causal discovery, what we can carry from one model to another is typically the knowledge rather than the specific instances of data, right? So as long as we ground our models with some fundamental principles and we are conscious, we know how to articulate those, these can be carried out from one domain to another, from one problem to another. Another concept or idea is compositional generalizability. So if we are capable of identifying some modular combinations of interpretability primitives, so if we are capable of learning representations, and those representations are common as a concept rather than specific to one instance or another, we can then systematically recombine them across different scales and across different domains. Another possible way to go about the domain disparity is if we look into systematic learning, right? Rather than asking an LLM or a Gen AI, create a model for me, great, you have a model. We can ask, generate a program, generate a code that describe a certain model. Now, the advantage in doing the latter is that I can now take that description that includes some of my background theory and maybe some other preferences, and ask another model to create such a model, right? So I'm taking maybe a step back. I'm doing systematic learning rather than generating models, but that is much more transferable. This is something that we can now have other experts scrutinizing what we have done and trying to figure out whether the assumptions we put inside are sensible, and it is much more transferable in that fashion. Another concept which was mentioned here in different versions is to incorporate feedback, right? So if we are capable of doing cross-domain validation, we can now bring a feedback loop and check whether some of the concept indeed transferred from one domain into another domain. So that was the first question. The second question was around universal explainability. So explainability relies on vocabulary. Different domains have different vocabularies. Can we come up with a generic explainability framework that transcends the separate syntax and semantics of vocabularies? So that goes a little bit into the linguistic side. One distinction that I wanted to make, and I hope that it makes sense to others, is we talk about explainability, we sometimes talk about interpretability, and sometimes some of us talk about derivability. And these are three different concepts. If we try to frame them, at least in my mind, explainability means that you have a decision and you make it maybe a post hoc explanation of that decision, right? Your system came up with an output. You want to explain what was that output to a human, right? Interpretability, on the other hand, is a model that you can explain to another person, this is the model and this is why it makes sense. Where derivability means that the model itself was formed in a way that is formally verifiable without any human, right? This is something that does not require any human approval for its consistency. So with that stated, one thing that we can try to do is to come up with a unified language. We heard a little bit about formal methods. So these are excellent means for us to, as a community, to come up with some consensus as for we will all going to use from tomorrow one system or another, and we will articulate all the theorems that we derive in that system. And once we do that, the beauty is that we can build up a collective corpus, right? So my theorem doesn't dust in a paper somewhere, but it can be employed by someone else, and your theorem can be employed by someone else, and that makes it more scalable as a community to build something. Of course, we can incorporate information theoretic machinery. We can bring algebraic geometry in order to embed theory and data in one unified space. And the other thing is we can bring some other notions from ontologies in order to bring the abstraction of, okay, we use a language when we define a model. We have operators, we have variables, we have programs. There is a Corey Howard definition of a program that also extends to algorithms and proofs, and it's not only models. If we try to come up with such a unification, it may help us to understand what we are doing in a way that is transferable. And once we do that, we can also build translators or mappings between one domain space and another. So that was my attempt to address that question. I have one more bonus slide. I hope that's not too much today. So I also noticed that we may talk about two different types of discovery as a community. One is Gen AI empowered simulation. So the physics or the knowledge is given, and it's really about exploration in some configuration space and trying to figure out what properties may be satisfied after we run such a simulation. Pins was mentioned, neural operators, physics-inspired, Hamiltonian neural network, Lagrange neural network, equivariant, and so forth. The other types of discovery is one where I think there was a question about Nobel Prize here and maybe some other question about getting an understanding of what those models are doing, is discovery when we have an unknown relations. And in that context, we can see how the scientific method has different ways of evolving, right? So we can start with hypothesis generation from the theory, verify empirically with data. We can go in the other direction. We can induce those hypotheses from the data. And we can try to do the reverse even. We can try to start from the knowledge, from the data, and try to combine them together. So I just want to leave this as something that we may want to consider as another paradigm for trying to bring more insight and understanding to the discovery mission. Thank you.
Thank you, Lior. Jag?
Thank you. So my name begins with the 10th letter in the alphabet. And in this panel, I'm going last in alphabetical order. Which is just pretty amazing. So I want to begin by thanking Bobby. Glad that you're here in this session, Vipin, and the other organizers for really fantastic 2 days. I had two specific questions to address. The first, to talk about uncertainty, safety, hallucinations. These were topics that came up repeatedly in the presentations. And what I thought I would do is, rather than me trying to build a theory of all of this, just quote some of the things that other people said that I thought were really insightful. And so these are things that I think came up, are all comments that came up at least once in the words that I have here and in spirit in other presentations. So first, worry about out-of-distribution data. Okay, this is something that I think we all have. Rare cases came up repeatedly. There is a need for uncertainty quantification. A more general way of thinking about this is that we need validation methods. So there is a lot of worry about if your model works, you know that it works on some example and you have no idea about anything else. And if you have statistics, there's at least some theory of what the error bars are and what the significance is and things of this nature. Explainability and interpretability, we just heard a lot of a careful analysis of from Lior. My one bullet point on that is A shortcoming of Gen AI that a lot of people are thinking very hard about is the inability to engage in symbolic reasoning, in decision making. And a particularly telling comment from this morning was that these models provide even less insight than computational models, which already are disappointing in their ability to provide insight, even though they've been used for years. Okay. I want to move on to the next question, which is also about other challenges. So this is now compliance, fairness, etc. So the first comment is, it doesn't matter how good the science is if the people responsible for using it or deploying it don't trust it, it isn't going to get used. And this was particularly emphasized in the agriculture panel yesterday, but I think that it came up in a lighter way in many other contexts as well. There was discussion, sometimes directly and sometimes indirectly, about the training data. And in particular, that the quality and the diversity matters. There was things like we should be able to consider diverse data types, new data types, multiple modalities. The way that people talk about this varied. What diversity means can vary a lot. It can be in types, it can be in demographics, it can be, in many different ways. There was issues of multi-resolution, multi-scale came up repeatedly. These are important things. These are tunable parameters in computational models that people use to trade off performance for accuracy. It isn't clear how you would use these as parameters in Gen AI models. And then there was some discussion about being able to address outliers, being able to address small minorities, things of this nature, which overall aggregate error metrics tend to cause models to ignore. It was already mentioned by one of the other speakers, I think Jarvis, that training data in science tends to have only positive examples. We should figure out how to have negative examples. And this is certainly true if the science that is being used to train your model comes from publications. And we think of scientific publications as a really good source of training data. And then there were complaints about limited controllability of models in scientific contexts. Right, okay, so these were the two things that were assigned to me, and then as I was going through, it appeared to me that there was a question not on Vuk's original list that I thought I'd also do, which are, what are the cross-cutting challenges across domains? Basically, my observation over these 2 days were there were people experts in many domains, and they would talk about why their domain was challenging. And then one would hear very related challenges in a different domain. It's not that the challenges are the same, they're not, but there are similarities, and I thought it'd be interesting just to talk about them. We talked about trust and explainability as something that leads to trust. We talked about heterogeneity, and this is heterogeneity in the data and data types, but we also talked about heterogeneity in models and methods. There was perhaps the one point that got said the most was that data are often skewed and data of interest. Some data of interest may be very limited, very sparse. We've got to deal with it. A thing that was said actually more yesterday than today was that labels are expensive and are often not available, and so reinforcement learning is important. I think the issues of outliers and singularities of various types came up repeatedly. And again, just to remind people, since we talked about that quite a bit today, yesterday when we were talking about, for instance, hydrology, there was a question of, some small land feature can make a huge difference to how things flow and collect. In almost every domain, real-life testing is expensive and slow. And this obviously constrains what one does. So two things. One, this seemed to be the case for many domains, but this is not always the case. Where it's not always the case, we have high throughput setups that are possible, right? So in biological sciences, this started a couple of decades ago in terms of high throughput experiments changing the bench. Today, in certain areas in chemistry, that is beginning to happen. But for most of the other domains that we were talking about, real-life testing is just not something that's easy to do. And what that means is that you've got to have good models. The models really matter. Digital twins are important. You've got to prove things out in silico as far as one can. Finally, there was some discussion of human-AI interface and how to split responsibility, how to divide the larger problem into things that the Gen AI systems can do well and that humans can do well and in a complementary way. That was mentioned today, and I felt that this was actually an important point that applied to everybody, even though in some of the discussion, particularly yesterday, it didn't come up. And with that, I'm going to hand it back to Vuk.
Thank you very much, Zach. So given the theme of this workshop, I thought it would be very fitting to ask Gen AI what it thinks about itself. So I fed an earlier draft of these slides to one of the large language models and asked it to produce 4 bullets. And this is what it came up with. I'll let you read those. I think I wouldn't necessarily prioritize them in the same way, but I think they're reasonably fitting. We are rather overdue, so let me ask if there are any pressing questions or comments or other thoughts on the synthesis of what you've heard today. If not, I think I'll just say thank you very much to all of our panelists. I know it was not easy to do this over the last couple of days, and we really appreciate your hard work. And I'll pass it back to
Yeah,
Vipin.
and again, reiterating, Vuk, this was an amazing 2-day meeting and made possible only because of your participation. And the synthesis panel idea sort of was added towards the end. And I'm so glad we did it because we got to learn the wisdom from all of you, so much more information than we would have done otherwise.